joint work with Or Meir on lifting within our function polynomial discrepancy. This talk will be about lifting theorems, but in order to motivate our work, we first state the direct sum question. The direct sum question asks, does solving n instances of a problem takes n times more resources than solving one instance? This question has been studied extensively. In some models, the answer to this question is yes, such as in query complexity, in information complexity, and non-deterministic communication complexity. A variation of the direct sum question is the XOR lemma, defined to be the following question. Given a Boolean function, g, thus calculating the parity of the outputs of g on n instances take n times more resources. This is also known to hold in some models. We now introduce a generalization of the previous questions, lifted problems. Let G be the communication problem with outputs 0, 1, and F be a function on binary strings. Then, the lifted problem is the following communication problem. Alice gets n inputs, x1 to xn. Bob also gets n inputs, y1 to yn. Let Z be the string achieved by applying G on each pair of xi and yi. Then, Alice and Bob want to compute the output of f on the string Z. We call the function f the outer function, and g the inner function. As we said, lifting is generalization of the direct sum as well as the XOR lemma. We'll see now that by fixing f to the identity, one gets back the direct sum question. Second, by letting f to be the parity function, we get the problem of the XOR lemma. Before stating what a lifting theorem is, we'll need the following notation. We denote by DCC and RCC the deterministic and randomized communication complexity. And similarly, we denote by DDT and RDT the deterministic and randomized query complexity. The claim of lifting theorem is that the communication complexity of the lifted problem is at least the query complexity of f times the communication complexity of g. As discussed earlier, lifting is a generalization of the direct sum question. Now, we can see that indeed, by letting f to be the identity function, the claim of the lifting theorem is that the communication complexity of n copies of g is at least the query complexity of the identity, that is n, times the communication complexity of g, that is as in the direct sum question. The same goes for the XOR lemma. We note that there are other forms of lifting theorems, but in this work, we'll focus on this form. So, why are we interested in lifting theorems? First of all, they have many applications. For example, in circuit complexity, in proof complexity, and more. Moreover, as we saw, they are natural generalization of the direct sum question and XOR lemma, where both questions have been studied extensively in many models, and thus, we believe that a generalization of both should also be of interest. Up until now, we state what a lifting theorem is. Now, we'll discuss for what function lifting theorems are known. The existing lifting theorems does not hold for all outer functions and inner functions. Most lifting theorems hold for all outer functions, but only for some inner functions, g. This is sufficient for most applications, as they mostly need specific f, but do not care a lot about the choice of g. We argue that it is interesting to prove lifting theorem for more inner functions. Specifically, we ask the following question. For what inner function g can we prove such lifting theorems? We have two motivations for this question. First, in the direct sum question, an important and natural goal is to prove the direct sum theorem for as many inner functions as possible. As lifting theorem is a generalization of the direct sum problem, we believe it's also important to prove lifting theorem for as many inner functions as possible. Second, we believe that having lifting theorem that hold for a variety of inner functions might lead to more applications. We'll now discuss for which inner function lifting theorem can be proved. To do so, we'll see some of the prior work and the result. In the deterministic setting, Raz and Mackenzie proved the first lifting theorem. Their lifting theorem holds where the inner function is the index function. Almost 2 decades later, Chattopadhyay, Kochki, Lof, Mukhopadhyay, and also Wu, Yao, and Yuan proved lifting theorem for inner products. Their work was motivated by finding an inner function with much smaller input size. The result of Chattopadhyay et al. Also holds for much more general family of inner function. Inner function that satisfies some heating property. Later, Chattopadhyay, Filmus, Kurth, Meir, and Pitassi prove lifting theorem for all inner functions that have low discrepancy. In the randomized setting, only relatively recently, Kurth, Pitassi, and Watson prove lifting theorem for the index function. Later, Chattopadhyay et al. Proved in the latter work a randomized lifting theorem. This lifting theorem holds for all inner functions with low discrepancy. In what follows, we will focus on the last work of Chattopadhyay et al. As our work build upon the work. As mentioned in the previous slide, the work of Chattopadhyay et al. Use a well-known complexity measure called discrepancy. It is convenient to look at instead at log of 1 over the discrepancy, which we will denote by delta of G. This measure gives a lower bound for the randomized communication complexity. In order to state the result, we recall that B is the length of the inputs of the inner function, and N is the length of the input of the outer function. Then, the main theorem of Chattopadhyay et al. Is both deterministic and randomized lifting theorem that holds for all inner function G such that B is bigger than log N times some constant, and delta of G is theta of B. Then, it holds that the communication complexity of the lifted problem is at least the query complexity of F times delta of G. Note that as delta of G is theta of B, the theorem only holds for inner functions that asymptotically have maximal delta and maximal communication complexity. Our work followed the work and generalized the results. In our work, we removed the requirement that delta of G is theta of B. Our main theorem holds for all inner functions with delta G that is at least log of N, and in particular is independent of the input length B. Thus, for any such G and any F, we get that the communication complexity of the lifted problem is at least the query complexity of F times delta of G. In the rest of the talk, we'll discuss some of the main ideas of the proof. For simplicity's sake, we'll focus on the deterministic case. The randomized lifting theorem is proved using similar ideas. Let's first recall what a lifted function is. Alice gets n inputs, x1 to xn. Bob also gets n inputs, y1 to yn. By applying the communication problem G on each pair of inputs, xy and yi, we get a string. Then, Alice and Bob want to compute the output of f on that string. In order to better understand the proof, we will first look at the upper bound for the communication complexity of the lifted problem. We note that there exists a natural protocol for solving lifted problems along the following line. Alice and Bob simulate the best decision tree for f, and every time the tree needs to do a query of the ith bit, they will just compute the best protocol for G on the ith inputs. The communication complexity of that protocol is equal to the query complexity of f times the communication complexity of G, matching the lower bound of the lifting theorem. We use this protocol as an inspiration for the lower bound. The proof of the lifting theorem shows that every efficient protocol for a lifted problem must behave like the natural protocol. Following previous work, we showed that, given a protocol that solves the lifted problem f composed on G, we can construct a decision tree for f. This is done via simulation argument. That is, the decision tree reconstructs run a simulation of the protocol for the lifted problem. More specifically, on input Z, the tree simulates the protocol on uniformly chosen inputs A and B, such that G to the power of n of A and B is equal to the input Z. The tree runs the simulation by querying Z when needed. At the end of the simulation, the tree returns the answer of the simulated protocol. Assuming the protocol returns the right answer, then this is an answer for f composed on G of A and B. This is equivalent by the definition to f of G of A and B. And by definition of simulation, G of A and B is equal to Z. Thus, the tree gives the correct answer to f of Z as we wanted. In order to simulate the protocol, the tree maintains two distributions of the inputs, x and y. As the tree simulates the protocol, it preserves that x and y are consistent with the current transcript at every given moment. We want to describe some structure of the input. But before describing it, we need the following definition. We say that the distribution x is dense if, for every subset I of the coordinates, the mean entropy of xi is high. The tree preserves the property that x and y are structured. That is, we can split the coordinates 1 to n into two parts, the fixed coordinates, such that for every fixed coordinate I, it holds that g of xi and yi is equal to zi. And the free coordinates. These are the coordinates such that the simulated transcript does not give a lot of information about them. This is captured by the notion of density. Note that, intuitively, the structure we introduced resembles the structure of the natural protocol. The fixed coordinates are the coordinates on which the protocol computed G, and the free coordinates are the one on which the protocol didn't talk. As the tree runs the simulation, the simulated protocol might transmit enough information about some set of coordinates I so that those coordinates are not free anymore. To preserve structure, we need to fix this set of coordinates. To do so, tree queries Z on the coordinates of the set I and condition x and y on the event that g of xi and yi is equal to zi for each coordinate in the set I. Intuitively, this corresponds to the case where the protocol just computes g on the coordinates in I. But this may lead to the following problem. The condition that g of xi and yi is equal to zi gives information about x and y and may lower the mean entropy of the free part of x and y. Thus, violate the density of x and y. This problem has been solved by Chattopadhyay et al. At their setting. Thus, we first introduced their solution. Their solution analyzes the problem for specific values of x. Thus, for every value x, we denote by e of x the event that g of xi and yi is equal to zi. First, we know that the problem is caused by certain values x, such that the y condition on this event is not dense. Such values are called sparsifying values. The main observation made by Chattopadhyay et al. Is that most values are not sparsifying, and thus, to resolve that issue, tree just removes sparsifying values from the support of x and y. The main lemma of Chattopadhyay et al. Essentially says that if x and y are structured, then the probability mass of sparsifying value is very small. The main obstacle in proving our result is that, unfortunately, the lemma of Chattopadhyay et al. Does not hold in our setting. We show that in our setting, there is an example where almost all values are sparsifying, which rules out this kind of lemma. Instead, we take a different approach. In our setting, it might be the case that all values are sparsifying. Thus, it is inevitable that y condition on this event will be not dense. Thus, we need to restore the density of y. As the distribution y is not dense, then there exists a set of coordinates j such that yj has low mean entropy. Therefore, exists a value y with high probability in yj. We say that such value violates density. We can solve the problem in the case where only a small number of values violate the density. We can restore the density of y by removing those values from the support of y. Our main technical contribution in this work is to show that in this case happen with high probability. We now state more formally our main plan. But first, we introduce the notion of recoverable values. A value is recoverable if the way we describe to restore the density is viable. Now we can state our main lemma that formalizes the observation. Our main lemma states that if x and y are structured, then the probability they take values that are not recoverable is very small. The tree we introduced in our paper remove in advance all values that are not recoverable. At some point along the simulation, the tree may need to fix some coordinates and condition on the x. If the distribution after the conditioning is dense, then the tree continue with the simulation. Otherwise, if all values are recoverable, we can now remove the value that violate the density from x and y and get then distribution, and then continue with the simulation. To warm up, in this talk, we started by discussing the connection between the direct sum question and XOR lemma to lifted problems. Next, we saw that Chattopadhyay et al. Proved the work a lifting theorem where delta of G is equal to theta of B. In our work, we generalize this result and only require that delta of G is bigger than log n times some constant. We then talk about some ideas from the proof. We saw that in our setting, all value can be specified, and therefore the main idea of Chattopadhyay et al. Cannot hold in our setting. Some different approach is needed. We suggest to recover the density by removing the value that violate the density. Then, we show our main lemma that informally show that most values are recoverable. Thank you very much.